Good morning, everybody. Since I have no idea how many people are listening, you will make sure that you send questions back to me on the Telegram channel, and it will be fed back to me then through an interrupt. Yeah, feel free to ask questions along as we go. Yeah. So good morning, everyone. This was supposed to be a lecture in front of a classroom. And for this mini course on cryptographic tools for distributed computing. However, since the virus has all caught us, not really caught us, but has all locked us up at home, we will do this remote via online system. So the goal of this mini course will be to give you an idea of how to use cryptographic tools and how to formally, precisely reason about what cryptography does. And for this, I'm going to assume you have a certain background in mathematics and in technology, which I presume is easy for everyone here. Now, the structure of this course is oriented in 4 different parts that will be grouped into the, let me just see where I have this. 4 different parts. First, I'm going to talk about basics of cryptography and provable security. Then I will introduce pseudo-random generators, pseudo-random functions. These are the basis of secret-key cryptosystems or symmetric-key cryptosystems. Then I will talk about public-key cryptosystems and how to use threshold cryptography. This is going to be the topic tomorrow. Threshold cryptography is a tool where we can implement the crypto system in a distributed way. There is lecture notes. There's an underlying textbook that will be posted in, well, that I did not write, but a colleague of mine, Mike Rosolek, wrote. It's called The Joy of Cryptography. That is the basis of this, and you will find this, the link online. Yeah. So just note here that today's lectures are going to be based on a textbook that is available online. That's called The Joy of Cryptography, and you'll find it under this line, under this heading, if you type this into your favorite search engine. Yeah. So let's start with basics of cryptography and provable security. And the idea, of course, is how you define that something is secure. Yeah. Provable security. First of all, the goals of crypto that you might have seen, yeah, goals of cryptography are threefold. We have CIA, yeah, confidentiality, integrity, and availability. These are the canonical goals, yeah. Availability. Usually, crypto research is only focused on the first 2. Confidentiality, how to keep something secret. Integrity, how to prevent that something is changed, yeah. And of course, for confidentiality, we will want to use tools like encryption, and also the pseudo-random functions I'm going to talk about today. Integrity, we use authentication, message and authentication codes, or, for example, also digital signatures. Availability is often deferred to other fields, maybe like distributed computing, where it actually talks about availability much more. Now, to start right away with the basic tool in cryptography, which is encryption. Let me introduce here the picture, the model for a cryptosystem, as introduced by Shannon already like 70 years ago, 1948, in a paper that founded information theory, or in a couple of papers that founded the field of information theory, but also was oriented towards studying and formally modeling cryptography. So a model of a secret key cryptosystem. Secret key because the key here has to be known only to the sender and the receiver. This model starts from the premise of a key generator. There is someone who generates a key for us. Yeah, this is going to be an algorithm in our formalization. In real life, it has to be a separate entity because this entity is going to know the key and is going to give the key to both participants of a conversation. And since the 70s, since public key crypto, we call the participants here Alice and Bob. So that they are going to have two algorithms here again. Alice, she will know a message. Well, before we do this, let's just write here that the key is what comes out of the key generation algorithm and is given to both. Alice sends a message to Bob. This message is going to be encrypted using an encryption algorithm, and Bob will use a corresponding decryption algorithm. And the encryption algorithm will produce something we call a ciphertext, C. The ciphertext is going to be sent over an unprotected wire, and Bob, with the help of the secret key, is going to decrypt this again. And so Bob will get an M out of here again, hopefully. And there's a third party, of course, that makes this all interesting, which is our eavesdropper, which is called Eve. And the eavesdropper will want to get information about the message M that Alice and Bob are communicating. So eavesdropper should not see the content of the message. And the question now is, how do we formalize this precisely? Yeah? How do we reason about what this security that we achieve here in this picture? Now when you want to formalize this, formalizing secret key encryption, yeah? This is this picture of the secret key cryptosystem. So here we're going to have, we can look at this as a mathematical definition of a secret key encryption system. That's a scheme consisting of three different algorithms, namely a key generation algorithm, as we saw. Then we have this encryption algorithm, and we have a decryption algorithm. And as we already showed here in the picture, yeah, the key generation algorithm is necessarily randomized. Everything in modern cryptography is randomized. Yeah, that's very important because you cannot get something out of a deterministic system. Yeah. So the key generation algorithm is not going to take any input parameters, but is producing this key for you. It's randomized and produces a secret key. That key is given to Alice and to Bob as shown in the picture. The encryption algorithm is going to take the key itself and a message M that Alice wants to send, and is going to produce a ciphertext. Yeah. Let me just write here that we are going to have some alphabet K where the key is from, M is from a message space, curly M, and the ciphertext is also from a ciphertext space. And the decryption algorithm is going to take our ciphertext and producing some M again. The question, of course, is the same M as above? This is what we will have to ask formally later. So the decryption algorithm here is deterministic. Also, the encryption algorithm is, generally speaking, randomized. And you will see why this is the case in a few minutes. Yeah. Now this is just algorithms. There's just 3 algorithms, and now we have to say what they should satisfy so that we can do crypto with it. And there are 2 parts of it, yeah, namely a completeness condition and a security condition. Completeness means that the scheme does its job, that the receiver, Bob, gets the message that Alice wanted to send. And if you are into distributed computing, as I suppose the majority of the audience is, then we call this completeness condition also, or this correctness condition, we call this also liveness, yeah? And the safety condition would be what we formalize under security condition, that nothing bad happens, where liveness means something good actually happens. We cannot really take these conditions, adopt these conditions from distributed computing verbatim to the field of cryptography, but there are always conditions that say something about the functioning of the scheme when everything works well, and there are many more conditions and more important conditions that specify what happens if there's an adversary in the system, and without an adversary, crypto is usually trivial. Yeah. So we can ask that this scheme here, an encryption scheme, we called it sigma, that this is correct. And correctness, or completeness, as I called it also, when for all the messages that we are producing and for all the keys, let me talk about the keys first, for all the keys that come out of the key generation algorithm, for all the messages that Alice may want to send to Bob, yeah, it holds that Bob decodes the ciphertext correctly with probability 1, yeah. And since we are doing a lot with probabilities, let me introduce already here the notation, probabilistic notation, yeah, namely that the decryption algorithm with this key here run on the ciphertext position here, and we are giving here the result of the encryption algorithm of M, that this outputs M again with probability 1. If I make a mistake, please tell me on the Telegram chat, and Petr will interrupt me, I'm sure, yeah? Since I'm writing, it's often the case also that I am going to introduce some typos here. So that's why I'm going to rely on you to tell me. So this is correctness. And you can think this is something like the liveness in a distributed algorithm, yeah? Security, this is what will concern us for the rest of the presentation. This is like safety, but it's much more important in crypto to talk about security than about liveness, yeah. And that, to the extent that even people in cryptography often forget that there is even a liveness condition to specify, that the scheme has to get its content to the receiver. An important aspect of the design of cryptosystems is that we make the specification of everything public, that we are only keeping private the key. You can see this in this picture here above, where the algorithms are actually known to everyone, and the formalization gives only the secret key, or leaves only the fact that the secret key is given to Alice and Bob only. You will see this, of course, in the security also. The security condition, this is known as Kirkhof's principle. I think a French cryptographer from the late 19th century who formulated after centuries of unsuccessful attempts to formalize cryptosystems that it makes sense to have two things, to distinguish two forms of keeping something secret in the cryptosystem design, namely that you will not keep the algorithm itself secret, but you only designate something else that's called your key, and you keep the key secret. Yeah. So you should design a cryptosystem such the algorithm can be public, and the security does not rely on the secrecy of the algorithm itself. So design a cryptosystem such that it does not rely on the secrecy of the algorithm itself. That means you have to have something else that is going to be secret, and this is what we call a key. Why is this a good principle? Because it's much easier to change this key than to change the algorithm in the first place. Yeah, it's also much easier to analyze when you have a family of keys, many different keys that you can use, and you can reason about all the algorithms that you get when you instantiate the main algorithm with the key, such that they are going to be different members of a family of algorithms. Yeah. So to give you an example here today, we are using AES, for example, with 128-bit keys. That means there are 2 to the 128 possible keys that in principle each specify a different algorithm. Did I hear some questions? Yes, you have to make some noise. Or type something that I can see.
Yeah, hello. Yeah, just a quick question, just to understand. You somehow equated correctness with liveness.
Yes.
But your definition of correctness looks like safety to me. I mean, at least from the formal perspective, you say that the decryption would give the encrypted message with probability 1. To me, it sounds like safety.
Okay, that's an interesting comment that we probably have to take offline, in the sense that okay, so
at least what we understand the safety from Lamport's definitions.
How should I say this? No, the system does not run forever, so you cannot rectify this again in the future. But what we can say here is that we are looking at the system, what it should give when we operate it under the sort of as it's intended, right? That something good comes out of it, namely that Bob in our picture, Bob gets the message. If we remove this condition here, then the systems that we can design under the formal notions are trivially secure because nothing has to happen. Yeah. So this is constraining our algorithms such that the receiver will get something out, namely here, we'll get this message with, we'll be able to receive, to get the message. We are not considering a process that, like a formal process model that proceeds forever in the sense of traces. Yeah. But that's why I'm saying we have to maybe take this for another discussion among experts.
Okay.
But
to me, it sounds a bit.
If you look at conditions in crypto textbooks and conditions in distributed computing textbooks, you will see that this condition here corresponds to the scheme achieving its goal, achieving something good. Yeah, and that's the intuitive reason for me calling it the analog of liveness.
Okay.
Sometimes it's called also completeness. Yeah, that if everybody is correct and operates the system, that then the message, the information is transported. Okay.
Okay. Thanks.
Good. Thanks. Then let us go back to Kirkhof's principle, and thanks for the question also. If we design our crypto systems such that they have separate things called keys, then we only need to keep these keys private and secret. And then, for example, if the crypto system is good, in the case of AES, as an American engineered, or actually as a Belgian engineered crypto system, that's now the American standard, has gone into a worldwide standard. We have a number of keys that is exponential in the so-called security parameter, which is 128 here. And that means it would take an adversary on the order of 2 to the 128 attempts to break the system by just trying the keys, and this should also be the best way the adversary has to break the system. Yeah, and to turn this around, the adversary can break this or find the key only with a probability that is going to be very small, namely 2 to the minus 128. Yeah, so this is an exponentially small probability, and we are happy when we design a system that has this feature.
Christian, can I interrupt you for a moment? So there is a question about the definition of the probability, whether the probability is 1 of the decryption, right? So the question is, since we have a limited randomness, does it mean it is not really equal to 1, but 1 minus something small?
It depends. We can design a crypto system such that the algorithm for encryption is probabilistic here and still satisfies this condition all the time. Yes. Usually the decryption algorithms will be deterministic. It is also possible to relax this notion, this one here, and say this must be at least 1 minus something called negligible, and we'll talk about this a bit more precisely. That's also feasible, but most practical provably secure crypto systems actually achieve this with probability 1. It will not be possible to achieve security with probability 1.
Okay, and
which does not depend on the length of the key.
Oh yeah, there I'm omitting a lot here. I'm omitting that security will depend on the probability of insecurity will depend also on the security parameter. Yeah, so on the length of the key, for example. Yeah, but this probability here in many practical systems, it can be 1.
Okay, good. So there is another question, but I think you will be covered it, right? That how to share the public key anonymously.
Yeah, this is a different topic. We are not talking about anonymity yet. We are talking much more basically about...
Not anonymity. I mean, how to share their public key without...
how to get the key across. Now, for the moment, we talk about secret key cryptography. So there is no public key that is going to be sent from the key generator. It's a key that must be kept secret, yeah?
Okay.
Okay, good. Let me continue and talk about the so-called one-time pad. That's a crypto system that originated, I think, 1917 with a guy called Vernam, but Shannon proved it secure only in 1948. It's also called Vernam's Cipher. And the security proof is by Shannon, 1948. This system here, this one-time pad crypto system is the ideal crypto system. It achieves so-called perfect security, and we'll also define this in a moment, but we are just looking at the system yet. Our messages and our keys are going to be L-bit strings or maybe lambda-bit strings, so our key space and the message space, and actually the ciphertext space as well, is going to be the set of lambda-bit strings. So it's going to encrypt a lambda-bit message with a uniformly randomly chosen lambda-bit string. So everything here is a lambda-bit string. And you can think of this as 100-bit or also 10,000-bit, but it's going to be cumbersome because you have to exchange 10,000-bit key ahead of time, yeah? So our key generation algorithm would simply pick. Now let me do an abbreviation here where I'm going to say that our, no, sigma we have already. Okay, let me not do this abbreviation then, okay? Let me just continue and say the key is chosen randomly from our alphabet. This notation here, this arrow, and then there is a set on the right-hand side of the assignment means choose randomly with uniform probability from this set, yeah, with uniform probability distribution. If there is on the right-hand side an algorithm, this might be also a randomized algorithm, and this randomized algorithm, of course, also gives us something that is randomly determined, yeah. So the key generation algorithm here in algorithm notation will just return this key. Then we have the encryption algorithm as we saw before. So we give it a key, we give it a message, and it is simply taking the XOR of the message string. The message is also a lambda bit string, and the key string. So it's going to take the key and XOR this as bit strings to the message. Yeah. And the decryption algorithm, that's of course exactly the same, because we can decrypt. We need the secret key again. We get a ciphertext C, and we also again we return the ciphertext XOR the key, and that is going to be to give us the message back. Why? Well, because we wanted to make sure that this condition we had here called correctness holds, namely that encryption, the decryption of the encryption is going to be the same as the original message. So the decryption under the key of the encryption on M is simply the key XOR the result of the encryption, which was the C XOR the message, and this is going to be back the message, because we know that the XOR of a bit string with itself is going to be the all zero string, and so we are going to get the message out of this. I think this is what I'm going to assume that you are all familiar with. Yeah. Now comes the actual thing we really want to talk about, namely security. How do we now prove, or not prove, how do we reason why this is secure? Let me just start to define security. So this was correctness, by the way, huh? Now about security, and for security, we first need to develop the tools to how we're going to define this, yeah. And what we are going to do is we are going to look at at a family of algorithms, at many different algorithms that attempt to guess what this message was. And in a more complicated setting, these other algorithms, they will want to break the integrity of our signatures, or they want to find out just the one bit about the long message, and so on. And in order to formalize this, we need some model of computation. In a very formal way, we model this with interacting Turing machines. We are not going to do this, but we are looking at the encryption scheme as a stateful library. This is what you know from programming. You are writing your program, and it is linked to a library. And the library itself may contain state. So programming speaking, it's like a static library that contains some hidden variables. You cannot access, as a program that uses the library, you will not be able to access the hidden state, the state of this library. So there is something that can be hidden inside. And when you write your application, you want then to generally find out whether you can break the security that is encapsulated by this library itself. But the rest of it is just like a library that you're used from an ordinary programming situation. And we will also be using tools like linking or composing programs with libraries. Yeah. So we are going to use the notion of a library. And this is the formalization that comes in this book of The Joy of Cryptography. If you look at other papers on cryptography, it's usually formalized through so-called oracles. Yeah, but this is not our topic here, or not our language here. So a library here is simply a collection of methods or functions and variables like state that are accessible to a private, I wanted to write here, private or static variables that are accessible to an application only through an interface. Yeah. To your program, to your application, only via an interface, and that interface is something that hides what lies below. Yeah, this interface, of course, has method calls. Yeah, and if you wanted to expose the value of data that is internal, then you have to give a method that lets you access this variable, like standard programming practice. Then, what we also do in programming, we can compose a program with a library. That means we can run a program with a library. And we just introduce a little notation for this, our linker, running a program P with, and of course this program P has to use the functions of the library, has to be programmed to be using these functions with library L is denoted by this linking operator, by this diamond operator, where we just compose the two like this. Yeah, this means also linked. The program is linked to the library. Yeah, and the second part of notation here is that this program might output something, and this is a right arrow. So if this program, whether it's linked to a library or not here, if this program outputs some value x, we're going to write it like this. Yeah, output some value x. Yeah, this program runs now. And what we will do now is say that we'll do later is to say that a program cannot know to which library it is linked. Yeah, because you are now then trying to write a program that covers a secret that is hidden inside the library. Yeah. Let us give an example first, a simple example of this only, namely a library L here that has, and I'm going to follow the pattern here of Rosolek, and I'm going to draw such boxes. The library internally picks something that we could call a secret, yeah, and it has a function reset. The reset function would reset the secret here again to a uniformly randomly chosen value. That could be a way that this program operates. And there is another function called guess, where the program might call this and try to find out what is the value, the current value of the secret S in here. Yeah. And the guess function here would simply return whether or not a Boolean, whether or not X is equal to S. Yeah? Now that's a library. We haven't done anything yet, but we have encapsulated a secret inside this library. This S here is something that now you cannot see from outside, but we can try to guess it. Yeah. And now we can write programs that try to guess this or try to find this. Yeah. Let's write a program that guesses the secret. Yeah. How do we guess this S? This could be a program A. Let me call this A. Program A tries to guess S. So this is a program that just picks a secret on its own. That's its guess for the embedded secret S, yeah. And then it calls the guess function with its C. It tests, sorry, no, it doesn't test, yeah, it doesn't test here. It basically only lets the library function guess test, yeah. And when we analyze now, what happens, of course, is that maybe it's time for the audience now to suggest answers. That you will probably see that the probability that A linked to our library L outputs true, that this probability is 2 to the minus lambda, because any C that we give here is going to match the guess inside only with probability 2 to the minus lambda, yeah? So this is a program that is efficient, takes one step, and guesses what the secret with probability exponentially small in lambda. We can also have another algorithm that tries to find the secret inside. This program here, of course, has to repeat many times. This program would repeat different guesses, yeah. We can also enumerate them. We could also pick all of them randomly, as I'm writing here. It repeats this until it finds one such that guess of X is true. And then it's going to return the X that it found. Now this program, of course, outputs always the correct X, yeah, and it is going to what can we reason about this now? We can reason about the probability distribution of the output itself, right? The probability distribution of when this program B is linked to the library here, that it outputs a particular valued set, yeah? That this is actually going to be also 2 to the minus lambda, because it always is the case that it outputs the secret that was embedded in the library here, the S, but it will actually output any particular string here with probability 2 to the minus lambda. This is an all quantifier over these here as well. So this would be two examples of, let's say, useless, relatively useless programs that use a library like this, but to show you that they cannot access the internals of the library here. Okay? Now we can try to define security with this syntax, yeah? And we are going to define an algorithm now that accesses a library, and we are going to look at whether this algorithm can look inside the libraries, can even tell what happens inside there. And if the algorithm cannot tell what that two libraries, it might be different, that the two libraries are different, then they are going to be interchangeable for the algorithm and interchangeable for our complete crypto system. Interchangeable will mean that the algorithms themselves, the libraries themselves, produce outputs with exactly the same probability distributions.
Christian.
Yes.
Sorry, just one remark. Could you clarify a little bit the last formula, the probability computation for B, or program B? Why is it? What exactly is the event, and what is the probability? Why it's 2 to the power of minus lambda?
The probability distribution here comes from the choice here, and from the choice made in the library L itself, yeah. And the statement here has to be quantified by all possible values, all possible outputs.
still isn't clear for me. For me, it should be 1 because you have repeat until, and if you guess true,
yes,
then
here this is 1. Yes, but we have now okay. The probability that we are outputting a particular value here is 2 to the minus lambda. We can make another statement here. We could say that the probability that B linked to L, yeah, we never, the S here is what we're trying to find, right? That this outputs S. This is 1. Yeah, this is a better statement.
Okay,
right.
I see. So this this Z is the random variable. Like, is random.
No, the Z is an arbitrary bit string. Okay.
Okay, so this is the probability of the S. Really, it is equal to the probability of S equals to Z, like, or
yes, this was
something like that.
This was this, right? Yeah, you're right. Yes. Clear?
Yeah,
you're right in pointing out that this is a better statement here. I did not. I camouflaged this a bit, right? this red, the written in red, is the more clear statement. Okay. Thank you for the clarification. Okay. Now we're going to look at 2 libraries. This is going to be a library left. We usually do left and right arguments here, and another library right. They are called interchangeable if they produce the same output distributions. And that means no matter what program we run, we link to it, we cannot find out any difference between them. Yeah. So 2 libraries are called interchangeable. And we are writing this with a sort of equivalence notation here. That namely, they are equivalent. Yeah. If we can already, I said they produce outputs with the same distribution. Let us have a more general statement that captures this as well, and let us look at all possible programs that we can link to these libraries. And if the output of any of these programs is the same, whether it is linked to the left or to the right library, and these outputs are going to be producing the same probability distributions, the same random variables, then these are interchangeable. Yeah, and we are going to restrict this again even to all the programs we can link to it with binary outputs. Yeah, so the 2 libraries are interchangeable if for all programs, and now we call these programs already A, and we look forward to these A's being adversaries, yeah, with binary output. This just is a simplification that makes this life a bit easier to specify what happens here. If we link this to the left library and that it outputs a 1, that this probability here is equal to when, oops, no, this was a mistake of the Apple thing. Okay. That this A is linked to the right library and it also outputs 1, that these 2 probabilities are equal. Here, we could now think of multiple different ways to implement our left and our right libraries. We could have code blocks that are not reachable in one, but are reachable in the other. We could have things that are completely different algorithm implementations. One takes much longer time, one takes less time. But as long as they produce the same values with the same distributions, if you interact with them, because it's stateful, then these probabilities that we get here, then this, and if these output probabilities are going to be the same, if the behavior of the library is the same, no matter how you interact with it, because you have a quantifier over all programs here, then these libraries will be interchangeable. Yeah. That means also we are not looking at our formalization here. We're not looking at side information, side channels like that, how fast it's computing or something like this. Yeah. Okay. So these are two interchangeable libraries, and they will correspond to perfect security because the two probability distributions are exactly the same. And now we can define security with this. For our one-time pad crypto system that we had before. The security we're defining here is only a one-time security. So we can use this crypto system at only once. That is actually what the one-time pad does. But it also simplifies our reasoning here quite a lot. Yeah. So our one-time secure crypto system, or our one-time secret crypto system, we call this a secret key crypto system that, as we modeled before, that we had already introduced here, our sigma scheme. It has one time security that we call also OTS, one time secure. If and only if this left library that we are going to call OTS-L is interchangeable with the right library that we're going to specify immediately. And these two libraries here are going to be libraries that let an adversary access the encryptions produced with with this crypto system, but only ever one encryption. Yeah, you'll see this right away. So the left library here, OTS-L, what does it expose to our adversary, to our application? It exposes only an eavesdrop routine. This is what Eve gets in the model of the crypto system before. Eavesdrop. And the eavesdrop method itself, the adversary can ask, or the adversary, the calling program can ask for two different messages to be encrypted, a left message or a right message. This is the library itself, okay? The left library here will encrypt the left message. So it's going to pick a key randomly from our scheme using the key generation. And then it's going to produce a ciphertext using the encryption method with the key and the left message here. Now, where is my color gone? Come on, here. This is important here that this is the left one. And then it's going to return the ciphertext, corresponding ciphertext. The other program here, the other library here, namely the one-time security right library, it is going to have the same method, also an eavesdrop method with an ML and an MR. It is going to pick the key in the same way as on the left side. So omitting this here, it's going to encrypt with the key. Go away. The right message. That's the difference between the two. So here we have the right message being encrypted, yeah? And what we are returning is going to be the same ciphertext, the same cryptogram. But now the question will be about, this is now the definition of our security notion here, that our crypto system sigma has one-time security, one-time secrecy, if and only if these two libraries, when operated like this, produce interchangeable, or the two libraries are interchangeable. Let me fill in the key generation here. I was expecting some question now, but apparently not, so maybe we can go on. Let us look at now what happens here, yeah? Why does our crypto system that we had before the one-time pad encryption method, why does this, it actually does ensure this one-time security? Could formulate this as a theorem, yeah? The one-time pad as one-time security. And let's look back at our specification here of the one-time pad. Here we go, yes? One-time pad. The one-time pad picks a uniformly random key and XORs this to the message M. Huh? Now, if you realize what happens here in the probability space, then for all messages, no matter what you do, the probability that well, I'm going to write this here. I'm going to write it such that for all the messages that we can pick here, the output of our encryption routine that picked the key uniformly randomly as a lambda bit string, and then returned this M XOR that key, this distribution over that is produced by this little code snippet here is the uniform distribution over lambda bit strings, yeah? So no matter what the message is, the fact that we added a uniformly random offset to it completely hides what was there before. So in particular, it implies that the output distribution of our left library here and our right libraries are exactly the same. Now maybe a good time for asking questions, if there are any.
Yep. So yes? I think people got confused by this eavesdrop function in the libraries. What exactly it is doing?
Okay, that's the crux. That's the important point. The eavesdrop function does not exist in your crypto system. Okay, your crypto system contains only the key generation, the encryption, and nothing else. The eavesdrop function is only introduced such that we can define security. So in order to define security, we need a formal notion, and we say basically our program, that is not a program that runs. This program here is going to be, the program here is going to be this A that we can think of as an adversary. Yeah? The adversary is going to access this eavesdrop function. Yeah, and our adversary is we don't want to make a statement about what the adversary does, right? That's why we say here, for all possible adversaries, yeah? This adversary can interact with our crypto system only through this eavesdrop function, right? It cannot look inside what happens here with the key, because otherwise we would have lost our security altogether, right? It can only interact with us through this eavesdrop function, yeah? And it's purely it's not mine, but it's purely my deliberate choice to call this eavesdrop, and putting functions like this into the libraries will make us give a model that appropriately respects the real-world capabilities of adversaries in cryptosystems. How we argue about this, that this eavesdrop is all it can do, this is up to us then to think whether our model that we have here matches reality. Yeah? But it's not a function that you can actually call. It only exists as a hypothetical tool to reason about the security. Yeah?
Okay. Actually, I think it's the first time you used the word adversary. So before you used it as a program, but now we understand that adversary actually is something, the entity which tries to break the property.
Let me say that the adversary is just a program, okay? The adversary is an entity, but since we are doing a formal model of what happens, our entity has to be modeled as an algorithm, right? And our entity is a program in the end of the day. If the adversary had like hypothetical powers, if the adversary could read your mind, we couldn't formalize it as an adversary, as a program yet. Okay?
Just 1 second. I don't know. I hope. So is the answer clear, or does it help? Maybe you can quickly react, or maybe it's going to be clear. Going to get clear afterwards with the example.
It has to be the case that this adversary, well, the libraries that we use here and the APIs that the libraries have, they are only for modeling security. They don't exist in the real world. Yeah.
Well, Eugen, I think we'll move on, and if it remains being unclear, come back.
Okay. An important thing about the formalization here will be that we can formulate this as a lemma if we want, that if two of these libraries here have the same behavior, if two libraries are interchangeable, then no matter what other library we add to it, they are still going to be interchangeable if we add the same library to it. That is, if a building block here, if one library, if two libraries are interchangeable, then we can add other code outside to it, and it will not make us able to see inside what happens any better. Yeah. Formally speaking, if we have two libraries that are interchangeable, yeah, and we have any other library L star here, for any other such library, it still holds that this L star composed with our left library is interchangeable with the L star, composed with, let me get our undo button here, with our right library. Yeah? And we can prove this, we're not going to do it formally here, but we can formally prove this by looking at the composed, at the adversary that actually tries to, at the algorithm that actually tries to distinguish this from this, hard coding the L star library into this adversary, and then relying on the fact that these L left and L right are actually interchangeable. Yeah. Okay, so this has been so far information theoretic. It has been purely probabilistic and not looked at the actual running times. And modern cryptography, however, is concerned with computationally limited adversaries, because this one-time path that we have defined here is not practical. Yeah? The one-time path requires that our key is as long as the message. Actually, Shannon proved this also. We're not going to prove this here. The reason for this impracticality is that it actually, we need keys that are as long as the messages, so we might as well exchange the messages. But of course, the keys were exchanged beforehand, before the messages come. So that's why in history, one-time paths, in the sense of little notebooks with lots of random characters printed in them, have actually been used a lot by spies. And up to the fact that spies tried to eat up the key material, the little code book, when they were about to be caught and things like this. Yeah. So this one-time path, I have to mention here, also has, I want to mention that this is called perfect security. Perfect security for a crypto system, because its ciphertext is statistically independent of the actual plaintext. This is what we asked for before, because you saw it already, because the libraries that encrypted this Eavesdrop function returns the same probability distribution no matter which message that we give it. Modeling computational security now. And that's going to take a step where we're going to restrict our adversaries. And then we come back to the question that was asked originally, where somebody objected that the adversary could just guess the key and then find out what happens, right? Here, you can also guess the key, but it will not help you, because you cannot test in the one-time path whether this key means anything good or not, because each possible plaintext message would be equally possible. Yeah. In the computational security world, we are now going to introduce a security parameter. It's going to be the same lambda parameter. And we're going to rely on the insights from computational complexity theory, that we consider everything that is polynomial time computable in a security parameter, or formally speaking, in the length of the inputs of a program, that everything that is polynomial time in the size of the data we're looking at, that we're going to consider this as efficient. And everything that takes more than polynomial time, we can call this super polynomial time. Exponential time would be an example of it, that this is not efficient. This is not feasible in our lifetime. For example, we cannot test 2 to the 128 possible keys, even with the fastest computers. And if because these operations just take too long. Yeah. And so we're going to model efficient computations, and we are as computations that are polynomial time in our security parameter, and we are going to restrict our calling programs of the libraries to those that are efficient, because our adversaries do not have unlimited computing power. They may have much more than we have, but the adversaries still are limited in their computing power. And this comes out to a large extent of the field of complexity theory, where one reasons about running time of algorithms. Algorithms are efficient whenever they run in time polynomial in that security parameter. Yeah? Their running time is polynomial in this security parameter lambda. So the security parameter here is an important concept, yeah. Means also that our notion here of polynomial, if we go a bit more formally, that is an asymptotic notion only. It's not really a practical notion. Yeah, we are going to say polynomial running time means that we have an exponent here, a positive exponent, yeah, such that for all a program inputs, x of length security parameter, yeah, so you could say that the length of x is lambda, yeah. Then the computation, the algorithm here, it halts after at most order, we have here lambda to the c steps, yeah, where we have to use a computation model like a Turing machine model, such that we can reason, we can count the number of steps that somebody does, yeah. And that includes every possible parallelization that you can have, because if you're going to run many different computers in parallel, then this is simply increasing your exponent here, but not necessarily, not as actually the running time beyond polynomial running time. So efficient algorithms are equated now with polynomial time algorithms, polytime algorithms, and we are all going to use the assumption that our adversary is efficient, yeah. To make some examples here, running time lambda to the 3, that's of course efficient. Lambda to the power of 1000, this is also efficient, yeah. It's just much less efficient here, but we still call it efficient, yeah. But something like 2 to the power of lambda, that's not efficient. But also we can have other more realistic expressions like something lambda to the power of log lambda. This is not efficient because this is not bounded by a polynomial. Yeah? These are examples of non-efficient or super polynomial time algorithms, if this is the running time of algorithms, yeah. And now this was about the running time of an algorithm when we talked about polynomial bounds on the runtime, and the dual of it, if we are going to our probabilistic world, is now going to be the probability that is either negligible or exponentially small if you want, or because a probability that is negligible is going to be defined as a probability that is smaller than any inverse polynomial. So a probability that shrinks faster than a polynomial fraction, than any polynomial fraction, yeah, is going to be a negligible probability that we don't want to care about, yeah, because as the example of the guessing algorithm showed us a bit earlier, you can always trade off probabilities of guessing with running times of algorithms, right? If you try twice, you're going to double the chance. Sorry, if you try to guess twice, so k times, you can double or multiply by k your chances of guessing right. And so we need also a statement about probabilities, yeah. So because we are going to look at our running times here, just as an example, an adversary that an adversary that has with running time that takes polynomial p of lambda steps, yeah, such an adversary may, of course, repeat a kind of guess p times and therefore increase its chances by a factor of p of lambda, yeah. Its winning chance by at most, yeah, p of lambda. If there's a basic probability that it succeeds, and for example, if this adversary would have to guess the lambda bit string from the beginning, right? The lambda bit string, then even with p of lambda guesses, right? We can only increase to p of lambda times 2 to the minus lambda, yeah? This adversary can increase its chance only to the number of steps that it takes, p of lambda times 2 to the minus lambda, yeah? And if we let our lambda grow asymptotically, this function here is asymptotically still vanishing. It is still going to be dominated by the exponentially small component. That's why we are now defining a function to be negligible if it vanishes when it's multiplied by any polynomial in our security parameter. Yeah? It's just a formal definition, but since you see this notion of negligibility so often in cryptography, it makes sense to have it written formally. Yeah? So a function like f is going to quantify our probability, for example, of winning. We call this negligible. Whenever this function asymptotically for all polynomials p, it grows, it still goes to 0 in the limit when we have our security parameter increase unboundedly, then our function, our polynomial times our function here, the limit of this is going to be 0. That means function cannot get significantly above 0, no matter how many, with which polynomial we are going to multiply this. So this will capture the fact that our adversary can try a polynomial number of times. Yeah, a function that is not negligible, we sometimes call it noticeable. Yeah, and then we can also define when two functions are close to each other and two functions are negligibly close to each other. So we're going to write that two functions p, and we can say this is going to be p of lambda is going to be negligibly close to q of lambda whenever their absolute difference is a negligible function. So when p of lambda minus q of lambda here is negligible. Okay, a lot of notation for the moment. Yeah? But we want to use this to get to defining more properly what is security for practical crypto systems. Yeah, and that notion of security notion is now called indistinguishability. It's not interchangeability anymore. It is indistinguishability. Yeah. And it will mean that we have two libraries where the output probabilities are going to be negligibly different only, yeah? Not the same output probabilities, but only negligibly different output probabilities, yeah? So recall that interchangeable libraries, they produce equal output distributions. And our indistinguishable libraries, they shall produce essentially the same probability distributions, where essentially the same means now that they are the same up to negligible differences, up to a negligible difference. Yeah. So in this indistinguishable libraries, they will produce essentially the same distributions. And let's just make this formal here and define that two libraries, left and right again, they are indistinguishable. And we are going to write this with the notation like this, with an approximation symbol with 3 tildes here. Whenever we are going to link them to any possible polynomial time adversary, any possible polynomial time algorithm, and the probabilities that the algorithm creates a different output from when it's linked to the left or the right library, that these probabilities differ only negligibly. Yeah? Whenever here, for all probabilistic, we have to say, and polynomial time, so these are all efficient algorithms A that we can link to our library, yeah. And again, our algorithm A here outputs only 1 bit, and A linked to our left library outputs the bit 1, and A out that I think we defined the notation here. Yes, that this is the notation that they are producing essentially the same distributions. So that these two functions are negligibly close, sorry. So when we're linking this now to the right library, that these probabilities are only negligibly different. Yeah. So now we have formally established a notion for two libraries behaving essentially the same if we are looking at them from a probabilistic and polynomial time algorithm, right? If we are an unbounded algorithm, if we were somebody who can compute exponentially many steps, then we could find a difference between the two. But since we are limited to polynomial time, we cannot find such a difference between the two. And maybe now is a good moment to pause and ask for questions, or?
Well, it looks like everything is clear. I don't see any questions for now.
Also clear for you?
For me, yes.
Good, okay. Very good. What we can do additionally here now is realize that these notions so far, they're going to be very handy and convenient, because there's this notion of indistinguishability here. This notion is, for example, symmetric. Yeah, if we have one library that is indistinguishable from a second library, then it follows also that the second library is indistinguishable from the first library. Yeah. It's also transitive. Yeah, and that again would have to be reasoned formally by looking at this. So if the first library is indistinguishable from a second, and that second library is indistinguishable from a third, then it follows that also the first library is indistinguishable from the third library. And these are going to be very handy properties for doing proofs. All of modern cryptography is full of such proofs. Because we want to reason step by step that something bad couldn't happen, because this bad thing could only happen with a negligibly small probability. And then once we have eliminated the possibilities that all such bad things can happen, we get to an ideal specification where the adversary, our attacker, does not even get, does not see anything whatsoever. Yeah. The third property here that we can also state is that if we have two libraries that are indistinguishable, then we can link them to any other library, or that same argument as before, where we considered this library that we link to it as a part of the algorithm that calls them. Then for any third library here, it holds also that this third library linked to the first library, the composite library we get from this, is again indistinguishable from the composition of that third library with the second library here. And now, as an example, here, just two libraries that are going to be indistinguishable but not interchangeable. First library here has only an interface. Well, no, the first library here, let me think how this has to be written. Yes, okay, this library here contains a secret, yeah? The library has initially in a static code picked the secret X and lambda bit string, yeah? And then it exposes to you a function guess. And you can guess this by sending some S, yeah? And the library will simply return whether your guess is a Boolean, whether your guess is equal to this, yeah? The right library itself does not contain a secret, yeah? But it always tells you what you expected, namely that you guessed wrongly, yeah? So this one here just returns false. And as you now should be able to see, the left library here is indistinguishable from the right library, because if you're only expensing polynomial time, you cannot find what this lambda bit secret was inside, like the secret key. And so these two libraries are indistinguishable. The right one does not even have the secret key embedded, does not even have this X inside. So this is an initial step that we are going to use towards proving statements about cryptosystems, modern, using the formalizations of modern cryptography. I'm not sure. I'm seeing a big clock here that counts down, and it takes me about 5 minutes more. I have 2 minutes 30 left. Should we defer this to the second part, or should we go into overtime for a moment? What do you recommend?
I think it would be maybe a good moment to stop and have a break
Good.
and resume in the second half. Like,
good. Then we can resume
hour.
with this in about half an hour. That's good, because there's a crucial step that will allow us also to review a bit what happened here. Yeah. Okay. Any questions?
Just one. The questions. I'm not sure there is a question, but
there are no questions. There are no questions. Right?
Oh, wait a second. There's one question coming. I see someone is typing. Yeah, will come. But I would like to announce that the slides and the exercises, well, the notes of written notes by Christian are going to be put online, and the exercises, I think they are already put online. So you're welcome.
Well, the exercises are mainly drawn also from the corresponding textbook, so the exercises will require that you'll read a bit more about the background from than what I've actually presented.
The composition mark. So when you write L star composed with L1.
Yes.
So what exactly means?
Okay,
it means like
that means yes. So let me just we had a program that was linked to the library, yeah, and that's the composition operator, that we link, yeah, a program to a library. That was the notion we used here to link a library to a program, or to run a program linked to a library. However, you are right by pointing this out. We can also link two libraries, and this is going to be a program and a library that was L star, I think, and the second library that was our L2, for example, yeah. So this library, this thing here, if this was one box, this was our library. Oh, I don't have enough space here. Let me clean this up here. Let me move it to the other side. So this library down here is actually L star linked to the second library L2, yeah? Because you can link libraries inside, we can also link the whole program to the composed library then, yeah? That makes sense?
I hope it does.
This is an example of the duality of code and data that we have in computer science. Formally speaking, we can always interpret a program as a piece of data for yet another more general program. Yeah.
And there is maybe one last question. Is just about. I think it's a good remark. The L star in the definition of the in the lemma.
Indistinguishability. No.
It's in the last lemma.
Here.
Yeah.
Yes.
So should it be computationally bound? Should you say anything about this?
Oh yeah, of course. I omitted a lot of extra text. Yeah, this is also a polynomial time library.
Okay. Well, I think this is the last, the great moment to stop, and we resume exactly in half an hour.
Okay. I leave all the sessions open, and I just turn off the camera like this.
You can mute your microphone and camera, but come back in half an hour.
Okay, I'll just leave it like this. Okay, good. Thanks. See you later. Let's resume where we have been before. So you will be able to have these notes then later on when I hit print on my iPad. So you don't have to write and copy everything. But I think there's also a recording being made of this. We have in the first part today talked about formalizing algorithms and formalizing experiments that we can do with algorithms. And these algorithms that we experiment with, they can keep secrets because, for example, they could create a key and then use this key to encrypt something. And then you see only the ciphertext of what was encrypted with it. Now, to reason a bit, to give you an idea of how to reason a bit more precisely with this, let's look at how we can say that two algorithms, two libraries, two stateful algorithms encapsulated in a library, in two different libraries. How can we reason that they are almost the same, And it's particularly easy when we can phrase the code in the two libraries such that in one library there is a bad event that happens, and in the other library that the event does not happen. And up to that bad event, the two libraries are exactly the same. So that gives us a bad event lemma then. That's the last thing about this formal notion of indistinguishability that I wanted to introduce here. The question we are answering here is how can we say, or capture that two of our libraries are almost the same or almost equal, behave almost in the same way, except for some event that happens with low probability, except for some low probability event that we call bad. In the code also, we're going to abbreviate this by making a restriction and say, without loss of generality, there is a Boolean variable called bad in our code that is initially false, and is set to true only once. Set to true exactly once. It never changes its value again. And the code in which these two libraries differ is guarded by this variable bad. That means there is somewhere that says, if bad, then do this, code behind bad. Let me phrase this again once more later. This is the only difference between our two libraries. So let's just phrase this like this. There will be a place like this where it says if bad, then blah blah blah, and this is the only difference between two libraries. All the rest of the code is exactly the same. And with this, now we can first formulate our bad event lemma, and then later do an example. So what we're going to use of this, of course, is that if the probability that the bad event happens is negligible, then that our two libraries are going to be indistinguishable. So we can capture things like the adversary guesses our key here. Because if the bad thing happens and the adversary knows our key, somebody guesses our key, then all bets are off. But we want to say that this happens with only negligible probability. So here we have our bad event lemma, more formally speaking. Suppose we have two libraries, left and right. Both are going to be the same. Both use this bad variable, except for the code behind bad. Both are the same, except for code that is guarded by if bad, then blah blah blah. As we said it before, then comes the different code here that could be different. And then, if this happens here, for all our efficient adversaries, they cannot distinguish this with probability bigger than the bad event happening, right? Then, for all probabilistic polynomial time, or efficient, as we also call it, algorithms A that can call these libraries, yeah? For all our algorithms that may call our libraries, when the algorithm is linked to the left and outputs 1, and the algorithm is linked to the right and outputs the probability that it's outputting 1. The absolute difference between these two probabilities is going to be bounded by the probability that we set this bad to 1 in the first place, that we set bad to true, yeah? So at most, the probability that A linked to left, not outputs, but actually sets bad to true. Yeah, so we have a handle on this, yeah. Now you might say, why do we have the left library specified in here instead of the right? And the answer is it's arbitrary because the two libraries, left and right, they are equivalent up to the code that comes behind the guard where bad has been set to true. So that actually doesn't really matter. So we can add as a note here that the probability that in the left library we set bad to true for the first time, yeah, for the first time ever, not for the second time necessarily, but we only set it to true once, yeah, and we only look at here also at the first time we set this bad to true because we only set it once to true, that this probability is exactly the same as the probability that in this other library we set it bad to true. That's just because the only difference between the two is in there, yeah? Okay, with this, we're not going to formally prove this, but you can imagine how this will follow from the definition of negligible probability of bad, and that fact that this difference here between the probabilities is also the absolute value of the difference of the probabilities. As an example here now, let us look at a library. Let me construct this in a way where we're going to have a library in the middle that like two libraries in the middle that are going to use the bad, and then on the extreme sides we're going to have 4 libraries here that can show you how we use this as a proof method, yeah? So we could just have a library here that we're going to call hybrid left, and another one, this is a hybrid right. And we're going to do a lot of stuff with hybrid proof libraries in crypto because they're going to be between the left over here and the library right over here. This library itself, it exposes only one method. The method here is a guess method that we have seen before already. The guess takes a parameter, let's call it x again here, and it then picks a random L-bit string, lambda bit string, and it returns whether or not the caller here has guessed it correctly, yeah? Whether this is the same, okay? Now, this is the left library, okay? Now let's look at the hybrid library here, where we're going to expand the code a bit such that we have a variable bad, okay? Bad is initially false. And we also have a guess method here. And in this guess method, we do the same as on the left. Yeah, we are actually going to pick our random lambda bits string. And now we are going to test what is written on the left, but in a bit of a more characters. Yeah. If x is equal to s, then we can now set bad to true. We're respecting the syntax here, and we return. Actually, he guessed it correctly, so we're going to return true. And otherwise, we are outside here again. We're going to return false. So you see the code that is guarded by the bad. Well, there's no code yet. No, there's code that is guarded by this in the sense that it comes after that. Yeah, and it only happens equivalently to the fact that we set bad to true. Okay. So we can have now a second library where we're going to slightly change the semantics of this guess implementation. There's always a lot of writing involved with cryptographic formalizations, yeah. This library also picks a random bit string, yes. It actually also tests if x equals s, and then it also sets bad to true if the guess is correct, but then it doesn't do anything anymore. Okay, it just ignores the fact that it guessed correctly, and it always returns false. Okay, and so what happened here, let's just go one step after the other, is that here we have an example of code that happens if and only if bad is true. So the bad event lemma here is going to imply that these two here, the hybrid left and the hybrid right, are indistinguishable. Huh? Let's just go to the right-hand side and just ignore the bad variable again. Just program guess x, and in this case here, we're just not giving any chance for this calling algorithm to guess correctly, because we always return false. Okay, so we can see now that the bad event lemma was the reason why the left hybrid and the right hybrid were indistinguishable. If we look at the left and here at the left and the hybrid left again, then we are going to see that the semantics of the two guess implementations are exactly the same. The probability that we return true is exactly the same as in the hybrid left and in the left and the hybrid left. So these two are interchangeable. Same over here, right? Over here, it's not even possible for hybrid right to return true. So it always returns false, as does this one here. So these two are actually interchangeable because they are exactly the same input-output characteristics. And that means now we have shown that the left one is, in a more precise way, and using this bad event lemma, that the left library over here is indistinguishable from the right library. And we have eliminated, by changing the code, the possibility of the adversary to guess correctly here. Now is the time for a question, maybe.
Yeah, well, one question for me. I don't see any questions from the audience. If you come back to the statement of the bad state lemma.
The bad event lemma here,
so it
yes.
looks like you need explicitly you need to say explicitly that in these libraries, L left and L right, the bad event has has a negligible probability of happening, right? Otherwise, it doesn't make sense to say that the.
You're right. That's true. I've omitted here the second part of this lemma that would actually state this. You're right. Yes, the lemma does not say that yet, but it's clear that we meant this. Yeah, thanks for checking this. Yes.
Okay, there are no more questions.
Good. Okay, thanks for clarification. So then let me just try to build a few cryptographic primitives with this notation now. And that actually brings us to the second topic, that are pseudo-random generators and pseudo-random functions. A pseudo-random generator, also abbreviated as a PRG, that produces randomness but cannot do magic. Yeah, it takes an initial seed and expands this to a longer value that looks random to anybody who observes the output only. If you get the key, of course, then it does not look random anymore, because a pseudo-random generator is a deterministic function. Yeah, but it is what we all use to produce the randomness inside our cryptographic schemes. So a pseudo-random generator is one of the most basic crypto primitives. It's usually called G also. It stretches a short. Yeah, it's usually short because the output of the generator is longer than the input. Otherwise, it doesn't have a chance to produce randomness in that sense. It's not producing randomness, it only produces pseudo-randomness. Yeah. So it stretches a short seed, and that seed must be chosen randomly for operating it correctly, and we'll specify how this works, to a long or longer output, and typically it is a sequence of bits or a bit stream, and that comes because these pseudo-random generators are intimately related to stream ciphers. Yeah, for encryption. Yeah, the pseudo-random functions are going to be something different, so I'm going to come to this later. So to look at the pseudo-random generator now, formally, we are going to specify this as a function from lambda bit strings to lambda plus L bit strings. So we have a stretch. We have added L bits to the output that are not present in the input. So that's going to be a function from lambda bit input strings to lambda plus L bit output strings. Is a deterministic function, of course. But it still achieves the magic of producing seemingly random output. Yeah. So this is a deterministic function for which we have a following equivalent, not equivalence, the indistinguishability between two libraries again, and this is going to be the PRG library with the real one, and a second library which is the PRG random, which is in a way the ideal specification, which is a second library that will just output only randomness. Yeah, and we are going to ask for samples from this. We cannot ask arbitrary samples because this pseudorandom generator only runs once. Yeah, we give it a random seed and it gives us lambda plus L seemingly random bits. So let's program also these two libraries here. So the PRG real library and the PRG random library. The real library actually it allows us only one method to access. Yeah. No, query function, no parameters. All we get is we pick the random seed inside and we run the random number generator, the pseudo-random generator. So we pick as specified and we return G, random number generated, evaluated at S. This is going to be a lambda plus L bit string. And here in the ideal library, in the one that specifies from what the one on the left should actually achieve, here we don't pick any seed, but we are simply picking something that it should output, namely a random bit string of length lambda plus L, and we return this. We return this L. So this two random variables here that are produced by these query functions are going to be indistinguishable if and only if G here is a secure pseudorandom generator. Did I write already that this S is the seed? Yes, our S here is the seed. And interestingly, if we can only expand or stretch our seed to one bit longer and we achieve a pseudorandom output, then this is as powerful as one that doubles the output length, for example. Yeah. We don't notice. This is something that has been recognized in crypto research for a while. So, for example, we could have a length doubling pseudorandom generator. This is one that you can easily imagine that takes an L-bit seed and outputs 2 L-bits strings. Sorry, lambda, huh? So that L is exactly lambda. If we look at this length doubling pseudorandom generator, we'll realize that actually it produces only a very tiny fraction of the range of the function. The range of this is the set of 2 lambda bit strings. There are 2 to the 2 lambda such strings, but the range of G, that size, I mean the subset that is actually the range of it is only 2 to the power lambda, because we only have well, it's actually at most, yeah, but we would assume that there are no collisions in here, so that for each different seed, a different output results, yeah. So the fraction that we hit in the output space is negligibly small. It's only 2 to the minus lambda fraction. Yet still, we cannot distinguish that we cannot distinguish that G is producing this output from the fact from the other experiment where we pick this uniformly randomly. So we would have, for example, here this extremely small fraction that G, the range of G only produces, that the range of G divided by the set of all possible 2 lambda bit strings that this is actually negligibly small, yet still no, because we are assuming that for the PRG here, these are indistinguishable. Nobody can tell, no efficient algorithm can tell that this is actually the case. Yeah. We cannot give you real examples of how to implement this because that is going to be into would lead us into the construction of mechanisms and cryptographic primitives that are very technical and don't actually add a lot to the way that we reason about their security. It's also the case that to construct such primitives like block ciphers, stream ciphers, or cryptographic hash functions, the tools are not exactly the ones that we are looking at here. Okay, this tool here now can be used for encryption. Encryption in the sense of one-time encryption, but now with computational security that before we had defined an encryption scheme with information theoretic or perfect security where the two experiments, the two libraries were interchangeable. Here they're going to be indistinguishable because if we can calculate through all possible keys, we could find out that these are different. So we can construct a so-called stream cipher from the pseudorandom generator. We are not going to see yet why it's called stream, yeah, because we are going to use it only once as a one-time thing. Stream cipher, this here performs, as I said, one-time encryption. So what does this mean? As before, for a particular key and a particular key, we can use this only once. Yeah. However, we have a different thing here now. Our key can be much shorter than the actual message we are going to encrypt. And that means also we have computational security, not information theoretic or perfect security. And if our pseudorandom generator would output a very, very long string, and if we can access this piecewise, one piece after the next, then we can get our stream. We can actually use our stream here. Then we're going to use our key generator to produce us a seed. And then we're going to use this seed and expand the pseudorandom generator, expand the seed using the pseudorandom generator to encrypt one message after the other. That's why we are going to encrypt a stream of those messages. The actual encryption method is going to be simple because all we care about is the randomness of this output, and we can simply XOR this to the message when the message itself is also a bit string. Yeah. So the encryption operation is like in the one-time pad. Let me just write this and then show a diagram so it becomes clear. Encryption using XOR with the PRG output. Yeah? And so our PRG now will produce, based on an initial secret key that is produced by a key generator. As before, key goes here, key also goes to the receiver. They both can, on both sides of the communication, they can now actually expand. Sorry, I wrote P or G. I should have written G only here. Huh? So it's only G, okay. But this G is the P or G, yeah. This is going to produce a sequence of the outputs that we can just divide into blocks like this, yeah, into pieces. And for We can do the same at the receiver, piece by piece, or divide the key stream here into such blocks. And then Alice, who's sending here, has a message M1, and this is another string that has the same length as this. XOR this together, that gives us C1 that we're going to send over to the receiver. The receiver is going to take this, what is written here as C1, XOR its own piece of the key stream to it, and should get M1 back, right? Let's just call this M1 hat, but it's clear that if this key stream is this piece of the PRG output is the same as this here, we're going to get this back over here, the same M1, same for M2, C2, decrypt again with XOR and the piece of the key stream, and so on. Now, this is going to be the model of a stream cipher, how we are going to encrypt with a pseudorandom generator. Yeah. So the computational security comes in because the seed itself, the secret key, is much shorter than the length of the messages we can encrypt. We can operate this in an online fashion. That means we can send message 1 and subsequently message 2. We don't have to get the full output at once. For the security condition, we are going to think that we only use it once. Yeah. So we operate this PRG and the corresponding cryptosystem online, like an online algorithm that works in pieces. One message after the next. But for the security condition, we think that the PRG output is just a very long random output. Huh? So let's just formalize the security condition in a minute, but let me just argue informally that we get always the same message back that we encrypted, and it is followed by the determinist, by the fact that the key generator here, the key generator gave the same key to the sender and the receiver, and by the fact that G algorithm itself is deterministic. What actually is needed here is state. Yeah? If you use a stream cipher for encryption, then the sender has to know how many messages it has already encrypted, and the receiver has to know the same index, because otherwise we get a hiccup, yeah, where we are not going to encrypt properly. It also, this method does not offer any kind of integrity protection, because somebody who can interfere with the transmission here in the middle, and I wanted to make this red, and sort of like flip a bit here, could just cause differences in the output. Yeah. So we're assuming here that the adversary can only read. The adversary cannot actually write on the transmission channel. Okay. How to define now security for this? This is going to be a one-time security notion, or for one-time secure encryption. One-time encryption with computational security. And the notion is going to be the same as before for the one-time pad, the one-time encryption with interchangeable libraries. Here we have one-time encryption with indistinguishable libraries. Yeah. So a one-time, a encryption scheme that we can also again abbreviate by sigma. It consists of a key generator. It consists of a encryption algorithm, a decryption algorithm. encryption, decryption. It has on-time computational secrecy or computational one-time secrecy. Secrecy, yes. If there are two libraries that we're going to specify, one-time secrecy left is indistinguishable of one-time secrecy right, where we will have to restrict the length of the messages that we give to be always the same, right? The adversary is giving us a left message and a right message, and they are going to be restricted to be always of the same length, because now we don't have messages that are always, or we can also restrict them to be always of the same length, but then we cannot really model that we are going to allow longer and shorter messages, yeah? So we're going to have the left one here, and we're going to have the right one, and you already know what's coming, namely that this scheme actually has only one method in the security definition in the library, namely this Eavesdrop, where we give a left message and a right message. So also over here, left message and a right message, and as I said before, they have to be on the same length, the left and the right. We pick the key using the key generator of the scheme, and then we are encrypting and returning a ciphertext using the encryption algorithm with the key and the left message here. Yes, that's important. And here we do the same, except we are taking the right message that we are encrypting. And because now we can actually permit that they have different lengths, that's why we have to restrict them to be of the same length. And over here, we also return the same. So it's the same notion as before, except that we've now changed this interchangeability to the indistinguishability here in the condition that these two libraries have to satisfy, okay? To be formal, we can construct such a scheme from our PRG. And maybe there's a question, at least I hear some noise in the back, I'm not sure.
Just one short clarification.
Yes, go ahead.
So in the fact that you use now the word secrecy instead of security, does it mean anything?
Did I use
before security? You said one-time security?
Then this was a mistake. I'm sorry. That was one of, at least one of them is a mistake. Okay.
So which one?
Well, here we call it one-time secrecy. It's formally more the secrecy, yeah. But we can also call it security to mean mostly the secrecy of it, yeah. So I think we should pick secrecy. No, here you mean computation. Security is more an overarching topic compared to secrecy, yeah. And when I was talking about the perfect secrecy, I might have mistakenly interpreted as, or said, perfect security, yeah. But it's a bit like all of cryptography, where if you go and look up in a lexica or in Wikipedia, you see there is cryptology. And cryptology contains cryptography and cryptanalysis, yeah? Two concepts.
Okay.
Then you learn also there that cryptography is the science of encrypting, graphene, like encrypting. Cryptanalysis is the science of attacking it. And after the moment you have introduced this distinction, we forget it again in crypto research, and we call it cryptography, even when we talk about attacks, not necessarily always cryptology. And so here must be the same glitch where we more precisely wanted to say secrecy, but in an earlier condition here, I have apparently used security instead of secrecy. Thanks for remembering this. The formal notions, though, here, the left and the right libraries, they should be the same, okay? And please complain if this is not the case. Yes, okay. So the key generator would just pick our key randomly, actually not from this space, from the key space, and return the key. The encryption operation takes parameters, so I cannot omit them. It takes a key and a message, and the encryption operation now will return. So it has access to the key, yeah, because it's given here. It calls the pseudorandom generator, and the key XORs this to the message, and the decryption operator is exactly the same. That will actually take the key itself and XOR it to the ciphertext. And as we've argued before for the one-time pair, this is going to give us the same thing back, okay? Good, I see that we've spent about half of the second session now on this. So let me explain briefly how we can take a useful POG that only doubles its output and make a POG out of it that stretches its output to an arbitrary length. Yeah? Extending, because it's kind of okay to implement with bits and bit fiddling this POG that doubles the length of the seed. It's much more difficult to actually have some bit fiddling construction that expands it to a longer output, but there is a generic method to do this for which we can reason formally that this is the case. So extending the stretch of a PRG. So suppose we have given one that doubles. Let's construct one that computes an output that is n times the length of the seed and is still secure. As I said before, even appending one bit could already be enough, but let's suppose we are given one that takes a lambda bit seed and outputs 2 lambda bits, yeah? Suppose that this is a PRG, and now we want to construct one that we call H, or maybe HN, because we are going to have an n-fold increase in the length of the output. N times lambda. We're going to show, well, I'm not going to formally prove this here, but in the script, in the Joy of Crypto script, you can read the formal proof of how this is going to be proven, but let me just give the construction, yeah? So any ideas on how this could be done, yeah? How should we do this? Because we cannot evaluate this thing. We can only like clock it. If we can call G many times. And each time we call it once, we get a 2 lambda bit string out. And so if we look at this in a graphical way, this is our seed. gonna get something that is twice as long. Yeah. And the relatively simple idea that is also showing you why we produce this in a stream incrementally is to take this as 1/2 of it as the next seed, and this here is the actual output. Yeah. Sort of. Well, let's write it. Let's write it a bit more formally. When this is Si, then here we're gonna have Si plus 1, and here is an output part that we can output. So our h of n, we can construct it like this, where we take S0 to be the S that we are given, and then we're just doing for I from 1 n times we are producing a output part, namely Ti, and Si, our next seed. No, I switched this around. I'm sorry. Let me just flip them around compared to the picture. We're taking Si here to be the next seed, and Ti what we're actually outputting, okay? And we're evaluating this on Si minus 1, so we're stretching this, yeah? And then this operator here, this vertical bars mean concatenation of bit strings, and now we simply return T1 concatenated T2 up to Tn, right? We never, of course, well, here not, right? Here we're never revealing any of the intermediate S values, but it's actually okay even to reveal and to give the it would be okay to actually append this one as well, but then we don't have the n-fold increase here, only the n-fold stretch in the output here. Okay, so this is how we increase this, and the security proof exploits the fact that each time we use G again, the input is indistinguishable from a random input by the previous application of the pseudorandom generator. We can have this also graphically. Now look at it as a box H of n that will contain, let me have to move it a bit higher up here, yeah. This box H of n receives one lambda bit string as a seed, and now you come such diagrams that you often see in crypto, where we have the component G here that gets the initial S0, that would be, of course, here. Out here comes the seed S1 for the next application of G S1, and this part of the output goes straight to the output of H, and that will be T1 as we called it, and here comes S2, and T2 goes out here, okay? And so on, huh? So this is how you incrementally build this output into a n-fold increase in the length of the randomness that you're given. And this satisfies the properties that we have specified before. Okay? Any questions on this? Oh, no.
No, it doesn't look like. I think it's everything's clear.
Good. Good. So let's look at. I jumped away somewhere. Okay. Here. The pseudorandom generator you can only use one after each other, and this is not so useful in a sense. So let's look at the next higher primitive that we can build with this, namely the pseudorandom function. A pseudorandom function is a primitive that lets you access, in a way, lets you compute randomness of arbitrary values, because you can evaluate this on a particular input, and every time you evaluate at a different input, you get back a fresh random value. Pseudorandom functions. Pseudorandom functions, they correspond almost to block ciphers, whereas the pseudorandom generators corresponded to the stream ciphers. Yeah. So the pseudorandom functions also PRF, abbreviated as PRFs. They allow, if you want to say, random access to the function value. So that should be random access, as in the sense of random access memory, right? You can go and ask at any position independently. This is like a random access that you have to your disk drive compared to your tape. Yeah, the stream cipher is like a tape. You can only read from the start to the end linearly. In the PRF, you can go like an SSD or a disk. You can go at any point of the space. You can read it. Yeah, and it allows random access reads in that sense. Yeah, like a disk, where is the PRG, a disk memory, yeah, or disk storage space, whereas the PRG allows only sequential access, as if it was a tape. So the PRF is a much more powerful primitive. It's much more useful. In fundamental power, the two are equivalent. One can build PRF from PRG and PRG from PRF. Yeah, one direction is particularly easy. The other one is quite advanced. So we're not going into this, but we are going to be concerned with the definition of security for this. Yeah. So the PRF also has a seed. Let's call a secret seed. Let's call this a key now here. Key. And so for each particular key, we get a different deterministic function. Yeah. And this key, of course, is kept secret by the entity that operates this. So we can say, for example, that fk at position I would be the output of that pseudorandom function. Let me make this a bit more formal here. Let me write that fk is a function from in bit strings to out bit strings, yeah, so that we can talk about this. And what we actually have here is our algorithm, and here we have somewhere else this fk. It can query different inputs here. That's why I wrote I here. And each time it queries it at a different input, it gets back this value here, as if this implementation of the function here chose the outputs randomly. Yeah. So random looking outputs completely independently as soon as we are invoking this function or evaluating the function at some different input value. So formally speaking, of course, we can again model this with libraries. Yeah. So a pseudo-random function that maps bit strings of length in to length out. Well, now I wanted I think I want the key to be part of this as well, so that the whole thing, the whole PRF becomes a function. So we are going to add here as a first parameter of the function the key that has lambda bit length, and as a second parameter of the domain, going to have the input strings, and each such evaluation produces us a output bit string of length out. So this PRF f is a deterministic function that satisfies the following security notion that we're going to specify using libraries. Namely, that we have a PRF real and a PRF is either random or ideal. Let's call it a random library. And I already hinted at what should happen here. These two libraries are going to be indistinguishable, right? Then we have a PRF. Now we have to specify the libraries. But each time that we invoke this call to f, and we don't know the key, but the key is always the same, we are getting back a fresh output bit string that is of out bits long. Yeah. So this library here will initially, and when we ask for the same input again, we of course must get the same output back, right? That's why this library internally keeps like an associative array or a hash map, and each time we ask a different input, we are going to look into this hash map whether this has been there already. So this could be a lookup function, where we give it an input x, and we ask here if this has already been queried. Yeah. So if t of x is non-nil, then well, then we can actually just go and return this. Yeah. Let me formulate it differently here. Let me turn the semantics around, and let's say if this is nil, then apparently we've never queried the function on exactly this value. So what we have to do is to put some random value here, namely a bit string. Remember, this notation here means we are picking a random bit string of length out and putting it into, storing it into position x of this array. And we simply now are returning this value. So the first time we get this with the query for a location, we fill it, and later on we simply look it up. That's why it's called look up. Yeah. In the real implementation here on the left side, we are not going to have such a table, not going to flip random bits. We only have initially in the static initialization a key that is chosen, namely our lambda bits key, bit key, and our lookup function now is exercising f. So the lookup will simply evaluate f with the key k at position x, yeah, and then return this. We wrote it as if it was fk, but it's clear that this k is the first parameter of this function here with two inputs. Yeah. So if these two libraries are indistinguishable, then we are getting a function that actually looks random or is pseudo-random. How are we implementing this in practice? Does anyone have an idea? I talked about stream ciphers, there are block ciphers, and this is almost what AES, the block cipher, gives you. Yeah, if we take the key and put this key into where we put the key for the block cipher, then this is going to correspond to with output length the same as also the input length actually. Then this would be the way that we implement this with AES, for example, from a block cipher. Yeah, a block cipher is more. A block cipher is actually a pseudorandom permutation, so it's not a full function. Yeah? You can imagine how many such functions there exist. There are fewer permutations, of course, than there are functions, because the block cipher itself is also invertible. So a pseudorandom permutation would be a formal model for a block cipher. Here we're looking only at a pseudorandom function. That's the more generic primitive, however. So let's look at how to build such a pseudorandom function by saying how not to build one. Yeah, because I said earlier that it's difficult to build one. It's an quite involved construction from a pseudorandom generator. It can be done. So let's look at how not to build one as a motivation for the more complex topic. How not to build a pseudo-random function from a pseudo-random generator. Yeah, that's important here. Yeah, don't do that, right? So we're given our PRG, and let's just suppose it has also again lambda bit seeds, and it is a length doubling pseudo-random generator that will output 2 lambda bit strings at once, and we want to build a PRF that yeah, let's say also has lambda bit keys, lambda bit inputs, and it is sufficient to give it 2 lambda bit outputs. It could also be just lambda bit output, doesn't really matter. Let's just say it should produce 2 lambda bit outputs, yeah. And the simple idea that one might have is just to say we have this pseudo-random function on 2 variables, yeah, there's x. And so let's evaluate the pseudo-random generator on the key we are given and XOR. Oh no, I made a mistake because it should only be, it should be only lambda bit output here, okay. No, we wanted to, okay, let's just take, no, we wanted to XOR the input to it. Okay, so we're giving, that means we have to actually have a 2 lambda bit inputs here so that we're going to get 2 lambda bits of output. Okay, is this secure? Well, I already wrote that it's not going to be secure. So how can we break this? How can we distinguish that these two are, this output is not random? Because if you look at only one call to F here, yeah, it's clear that we are going to get something from G that looks pseudo-random. We don't disclose the key to anyone. The key is hidden from us. So we're going to get back something that is pseudo-random XORed to our input. So that should be also, again, pseudo-random. But the fact is it's not if we call it twice, yeah? Because remember, this here was a one-time secure encryption scheme. And if we use it twice, it's actually going to break. And the example is here. We could also call this a differential attack. Yeah, if we take 2 different inputs, x and y, and calculate what this is going to give us. In both cases, we're going to evaluate the PRG on the key k. Then we're XORing here x, here we're XORing y. So from this, we will know that our XOR of the 2 values namely this XOR the PRF evaluated at Y is going to be the same as X XOR Y, because the key stream here XORs out, but this should not be the case, so we can easily test by just calling this PRF twice and then checking whether or not the two outputs from the PRF would give us the XOR of the two inputs, whether or not this is the case. So this should hold in a true PRF, this equation here, only with probability 2 to the minus 2 lambda, actually, not lambda, 2 lambda, if F was a true PRF. Well, if F was truly random, it should happen only with this. Otherwise, it should happen only with a probability that is negligibly different from 2 to the 2 to the minus 2 lambda. But it actually holds always, yeah. Okay. Questions about this construction here? Or this failed construction? We're going to use the notion then of this later, and this a distributed implementation of such a pseudorandom function that we can use in protocols, but only tomorrow. Question? There was one.
I don't see any questions from the audience, but just to clarify, so you gave a wrong construction of a pseudo-random function, right?
Exactly.
So how about the construction which works?
The construction which works is going to be much more, is going to be more involved, in the sense that we'll have to go bit by bit through the argument and either take a left or a right path in a tree of evaluations of the PRG. We're going to construct a full tree of evaluations of the PRG. Indicate, or each time driven by the bits that are going to be specified by the input. So what we have to do here is avoid that we are evaluating, avoid that we are doing this, yeah, that we are evaluating this at the same position twice, yeah. We must do that, the G part at the same position, yeah, because pseudorandom generator, just like the one-time encryption, one-time secure encryption only, must each time be evaluated in a different piece, yeah, in a different input. And that's actually what this will construct. But we are not choosing any additional randomness. We are carefully directing the queries to G into a tree of all possible evaluations. Yeah, this is very intuitively, because technically it would need more space to write it down. The other direction is quite easy, right? The other direction is, given a PRF F, yeah, implement this, yeah. For this other direction, oh, yes, implementing a PRG from a PRF, that's easy because even we can have one with arbitrary stretch, right? So G, that should take our input seed lambda bits to say n times lambda bits, yeah? This is what we want, right? And if we have one that an F that actually produces Fk, well, with some x that takes also lambda bits and maybe again lambda bit here, produces only lambda bit strings. Then we just evaluate f on 1, 2, 3, 4, 5, and so on, such that we concatenate then the outputs together. Yeah. So we have here the binary representation of 1 concatenated with f evaluated again at the binary representation of 2, and so on until f of n. Huh? So that's how we get n. Sorry, no, this, yeah, here n times an output length from many calls to the one that is a pseudorandom function. And since we never call this on the same argument here in the second position, this is going to be pseudorandom from the definition of the pseudorandom function. Okay. That rounds up our treatment of symmetric key primitives. Going towards public key primitives now. Let me let's go away here. Yes. Let me now move towards public key crypto and a bit of number theory, because that would also concern us in the next session also of tomorrow. So it's going to be a third part called public key crypto, I think, yeah. And it's only the public key crypto primitives that we can implement nicely in distributed systems in such distributed sort of threshold protocols. The symmetric key primitives are weaker, are messier, they don't have such nice algebraic presentation, so they cannot really be implemented so nicely in distributed systems in a fault-tolerant way. And for motivating public key cryptography, again, we can talk about public key cryptosystems for encryption and also about integrity primitives. I'm not exactly sure whether we're going to get to public key signatures, but public key signatures are the primitives for integrity preservation. Public key cryptosystems, public key encryption is the primitive for keeping things secret. And now we can come back to the original question that was about how does the public key go from the key generator to all the entities, or what is the role of transporting the public key and the secret key. And here now in public key crypto, the main difference is that we don't have the same key for encryption and decryption. We have two separate keys. Yeah, we have a public key and a secret key. So let's look at the public key crypto system first. And if you remember, we actually only looked at one-time secure symmetric key cryptosystems or secret key cryptosystems. We use public key as a alias for asymmetric sometimes, because the keys are asymmetric, and we use secret key also as an alias or as a synonym for symmetric. Secret key in symmetric key crypto is also a synonym. So the public key crypto system now differs mainly in the key generation and in the way that the encryption algorithms work. Again, a key generation algorithm. The key generation algorithm now outputs a key pair, a public key and the so-called secret key. Public key can be known by everybody, but secret key only by the one entity that that has the power to decrypt. So you already see that the encryption method is now going to take only the public key and is going to produce also a ciphertext as before from a message, and the decryption algorithm is going to take a secret key only together with such a ciphertext. That's just like before, except not restricted to once, and is going to output something that might be a message again. Okay. And similarly to before, we can define completeness for our public key cryptosystem, namely that for all the keys that we generated here from our keychain algorithm, and for all messages in our message space that is as before, we have that the decryption with, oh, this was too quick here. This is not a single key. This is a key pair, namely public key, secret key. Decryption with the secret key of an encryption under the corresponding public key of a message M is going to give us the same message that we actually encrypted with it. So that's the, as I called before, liveness analog of the public key cryptosystem. For the security, again, we look at a notion formalized with libraries. And now here is a slight difference. Now we can call this many times. Yeah, now we're not only using it once, we're using it many times. So the second thing that will matter is what capability do we allow the calling program in terms of a library. Yeah? Do we allow it to do we allow this calling program to specify bit strings to decrypt, such that we can see the decryptions corresponding to a particular ciphertext that may not even be legitimate ciphertext, or do we only ask for encryptions to be produced and we are not sure which message is inside? This is either a chosen ciphertext attack or a chosen plain text attack. The chosen ciphertext attacks are much more powerful. We're not going to talk about them. We're only looking at chosen plain text attacks where we can specify a message to encrypt, and we're going to see what this results in. But of course, we may not be able to specify all the messages, so we are not going to specify only one message, so we specify two separate messages, the left message and the right message, and one of them is encrypted and we don't know which one, okay? So security is a public key crypto system that consists of these algorithms that we have specified before, is secure against a chosen plain text attack. So we can only specify M if the two libraries here are, so this is a PKCS, should we have here? PKCS, no, let's just call it PK, I think. PK, chosen plain text attack. Left library is indistinguishable from the public key chosen plain text attack right library. So I have to give you these two libraries here. Chosen plain text attack left, and the PK chosen plain text attack right. So these are going to be if these are indistinguishable, then our scheme is chosen plaintext attack secure. The library itself, it keeps state, it keeps namely public key and the secret key produced by the key generator as a state. Does not reveal it to the calling program. Yeah? What can you ask here? Well, since we are not revealing the key itself, I mean, from the library, the internal state, we have to give a method that allows the calling program to get this key, get the public key. So in this case, we are returning the public key. And also in the other library here, in the right one, we're doing exactly the same. We give it a method to extract the public key such that the calling program can, or the adversary can, on its own produce encryptions. Yeah. And then we have a test method. Yeah. Whether or not we can distinguish if the left or the right message was actually encrypted. And as before, when I give a left and the right message, then on the left library we are encrypting the left message, in the right library we are encrypting the right one. So here we are encrypting under the public key the left message and return that. And here we are encrypting under the same public key that is available to the calling program the right message. So that's the same as before, right here, left here, left message here. And that's all there is. This is similar, roughly similar to the methods before, except we have a new element here, and that was also at the basis of the formalization of modern cryptography that led to the led to the Turing Award of Goldwasser and Micali, namely recognizing that if I allow you to encrypt because you have the public key, this encryption operation here is necessarily randomized. Yeah? If the encryption was deterministic, I could just test if what is the ciphertext corresponding to ML, and I can then distinguish whether I'm interacting with the left or the right library, because I can recompute for myself because I have the public key. Yeah? So the paper on probabilistic encryption by Goldwasser and Micali was the first one to prominently and formally nicely point this out, and also introducing here the need for probabilistic encryption schemes. Of course, they went also on to formalize zero knowledge proofs and construct those, but the necessity of encrypting probabilistically is visible already here, because if I know the public key, then I can just re-encrypt here, and I get to see whether ML or MLR is encrypted if the encryption was deterministic. So in the symmetric key world, there is an analog of this, exactly the same if we are formalizing encryption schemes here where we don't give the public key, we still need determinism there. And in the symmetric key world, we are usually getting this randomization in through so-called initialization vectors or salts or concepts like this. In the public key encryption setting, we are inserting this, we are getting the randomness by randomized probabilistic choice of the encryption algorithm itself. I think in the interest of time, and it's now a good point to break so that we can talk about implementations of this in the next session that will happen tomorrow, where we are going to look at number theoretic primitives to implement this so that we can also extend these primitives later then to distributed implementations. Yeah. That would allow me now to pause and ask for questions.
Christian, there are no questions. Like as far as I also do not have questions, unfortunately. So
Okay.
for me, it was everything clear. So I think.
Good. Okay.
Oh, okay.
I think it's
Peter.
just because it's mostly definitions. It's yeah, so it's formalism. So it's I think it's yeah, there are almost no proofs and results. So concerning definitions, I think from my side, I think clear, and I think what I can see from the audience, it looks like they are satisfied.
But Peter, previously you have found a lot of mistakes there. Have you found during this part?
No, I don't. No, I think it's to me everything is fine. Don't.
We did not have so many. Let me just go backtrack here. We did not have so many.
I mean, not so many, but like Peter, each session have found some.
Not in my first part. You meant in the other questions.
Yeah, in the questions. Yeah.
Okay, there is a question. Okay. There is a question, and let me see. What about the verification of a message signed using a public key? I'm not sure I understand exactly the question.
Verification.
How a message signed with a public key is verified. Yeah.
That actually refers to the concept of digital signatures we did not talk about yet. Yeah. Concept of digital signatures is in a way the dual of public key encryption. We're gonna, in the implementation, they look relatively similar, but in the definition, they look totally different. And the definitions of the signatures and definitions of public key encryption, they are totally different beasts. And that's also how they have to be treated totally differently. So we are not going to look at it yet. We might be able to get there tomorrow in the session for we talk about verification using digital signatures. It is a method to provide integrity, such that we can verify that some entity, the one that knows this secret key here, has actually issued a signature on something. Yeah, I wanted to make a different color here. Did not want to go.
Okay.
Yes. The secret key will be used to sign. The public key will be used to verify if we're talking about signatures. Here, for the moment, we have only looked at encryption, and decryption.
So tomorrow will be even more interesting.
Well, tomorrow will be more, and then we'll go distributed also, yeah?
Yeah, well, cool. At some point we should go distributed. Okay, cool.
Well, it's difficult to understand the things without being... it's difficult to understand what is implemented distributedly without having the background. That's my reason for explaining the difference between the pseudorandom generator and the pseudorandom function so explicitly, because we will see how to implement the pseudorandom function distributedly, yeah?
Okay, yeah, great. Of course, it makes sense, and it's good that we have 2 sessions for this course.
Good, yes, yeah. So
3 sessions.
I will make
3 sessions.
It's more. There's also a Q&A session. I will make this available. I will send you a PDF of what I wrote here, because I can hit print on the iPad, and it will be easy to get this up. I'm not yet sure how it's going to look like, but it's either a JPEG picture that is like enormously high and very small, very narrow, or it's a PDF that is going to be chopped up arbitrarily into pages.
This is dangerous. Maybe a JPEG would be better. I don't know.
I could try both.
I was looking that Simon is trying to write something, but like I was hoping for the question, but like he stopped writing. So I don't know whether we will have questions left.
Maybe tomorrow then.
Yeah, maybe tomorrow then.
Good. Okay.
Okay. Oh, there is a question.
The last one, yeah.
Yeah.
So is there a reason to prefer this way of defining security that uses programs and linking compared to using definitions with oracles? Yeah, so there's an alternative formalism.
Oh, the definition with oracles is more technical. It's a bit like programming in assembly or programming a bit higher level. I'm using this formalism here that I did not invent, by the way. Mike Roselek invented it. To be clearer to programmers, to say what happens, because this idea of a library encapsulates exactly what happens in the Oracle style definition. Except there you have to talk all the time about Oracle calls and this kind of stuff. Here it's more compact, yeah, because we can have the notation of one library being indistinguishable with another library, as opposed to a scheme, and then you have to talk about the experiments in the definitions more carefully. Yeah, the notions are equivalent. Yeah, and then I mean you can look at the textbook by Rosolek here that I'm using as a background, and everything is formalized here using the libraries. You can look at the textbook by Katz and Lindell, for example, John Katz and Yehuda Lindell, where everything is formalized using the oracles.
Okay. I think we should stop now to give at least 1 hour for lunch before the discussion room of Michael's code, which starts at
okay.
3 p.m.
Sounds good.
Yeah,
okay.
And thank you very much, and we continue tomorrow.
Thank you. I will continue tomorrow.
Thank you very much.
Bye.